More.
First convince the audience that we know what we're talking about, we're fast and we know the pain, and we show some pain. Then show the solution. Ask one of the colleagues at the office, he made a nice presentation about mobile app, maybe the presentation. Try to show what you
You know what? I feel like first choosing Amsterdam as the first market because we think it comes everything. Because it means that's
The online game tool.
fly
Kan gaan hier zoiets. Ja,
I think that's
goed. Zet er een fiets neer. Dan
suffered so much. I had to call my reception downstairs. It was horrible. Oh God, what do I do? I had a service department. All different categories. Yeah. But, no, I think Attila was suggesting Wednesday, but Svetlana is not here.
Class section,
huh?
Work it out. Yeah, it's live. How else can you see it?
Thursday I can make it, Friday I can't. Thursday was fine, Thursday to do.
Yes.
Before that, tomorrow I'll circulate some ideas and some games. Yeah. You can add it
I'm really fine. I don't care.
I'm feeling bad.
Ja. I think it might be.
I think I'm good. Ja, gaat niet. Nou ja, januari mag ik er een nieuwe kopen. Dus nieuwe koop mag ik. Ik krijg €300 van ING op 2 jaar. En dan zit er 2 jaar hier. Ik zie er al 1 jaar zo uit. Ja, voor Samsung.
So, welcome. All have looked at the questions. So I'll go through the answers one by one. If there are other things you want to ask, just raise your hand. So this is the exam of last year. That was on 21st of December. So the exam will be next week, and we start only at 7. So not 6:30, but at 7 in the M building. So the first one is just let's say the 6 phases of the risk data modeling life cycle. So just have to fill in. So did someone actually do the exam? So we start with.
I'm sorry. I didn't know, so it's good.
So we first have the research understanding phase. So what is it that we want to answer? And so there's a question out there, and we want to answer this question using data-based methods. Then the second one, that's the data understanding phase. Then data preparation phase, that's the first phase, then the modeling, evaluation, and deployment phase. We actually only came up to here, so the first 3 phases, and then this modeling phase, modeling and evaluation phase, that's the core subject of the machine learning course, which will be, I guess, starting in February. March. So then, before operations that belong to the data understanding phase. So what's the first thing that comes to mind? Yeah. So first you want to collect the data. Then
use exploration.
Explore the data.
yeah, so have a look. Have a look at the data. So you collect it. Yeah, first look. And if you look at the data, what can you judge?
Quality.
The quality of the data. Whether it's you need to do a lot of pre-processing or not, so whether there are outlining. And once you have assessed the quality of the data, then you could look for interesting
Subsets on the data.
yeah, subsets on the data. Okay, so these are just 4 operations. Then comment on the statement, data mining will automatically clean up messy databases, I guess.
Fully correct.
It should be.
I have an answer
If
here.
that would be the case, then a lot of people would be out of business. So, usually, well, the database could be old, and to clean up things, you have to decide upon several things, and such decisions will usually be driven by, for example, the modeling, the data preparation phase. And so, cleaning up whether something is messy or not actually is determined by the next phases. Then the next question. The next question is a very simple one. So we have 10 observations, and to make it even easier, I just thought I'd take the numbers 1 up to 10. Yeah, so these are the rank numbers. So the 4th observation is also equal to 4, but I just replaced the first and the last one. Yeah, and we can clearly see that the first and the last one are, in a sense, outlying observations, yeah, because they are quite different. So I also applied the sample mean and the sample standard deviation. So the first question is based on the Z-scores. Does this data contain outliers? So first of all, you should remember when is something based on a Z-score an outlier over here. So when do we consider an observation an outlier based on the Z-scores?
When
Yeah.
first we make the assumption that our data follow the normal,
Yeah.
then plus minus. We have this 3 sigma rule, and
Yeah. So if the absolute value of the Z-score is larger than 3,
yeah.
then it's considered an outlier based on the Z-scores. Yeah.
Yeah, first it's assumption that data should follow the normal distribution.
Yeah, but that's not the question that is asked. So here it's just asked, well, if you use this Z-score rule, when will an observation be an outlying observation? So Z-score is larger than 3 in absolute value. So what some students did is they calculated the z-scores of all these observations. Is that wrong? Not necessarily, but it's highly efficient because they are ordered. So this will give the lowest z-score. The last observation will give the highest z-score, and if both observations are not outlying, then also the intermediate values are not outlying. Yeah? So the first thing we do is we calculate the z-scores of the smallest and the largest observation, and then just judge whether the z-score, look at whether the z-score is larger than the absolute value. So the first z-score, that's just this 10 minus the sample average, 5.4, and we divide by the standard deviation, 7.397. And this gives us just a number. In this case, this number is negative. So it's minus 2.082. It's minus. Okay, it's minus 10, because otherwise it wouldn't be negative. In this case, we see that the absolute value of the z-score is not larger than 3. And therefore, this is not considered an outlier if we use this z-score rule. So then we can continue with the last observation, because this observation will have the highest z-score. And in this case, it's 1.974. And again, we see that the largest observation, the absolute value, has a z-score which is smaller than 3. So according to the z-score rule, this data doesn't contain outlying observations. So anybody has a guess why the z-score doesn't recover minus 10 and plus 10 as outlying observations? If we look at the standard deviations. Yeah, so the standard deviation is quite large. So if you would think, if this would be the numbers 1 up till 10, yeah, then the standard deviation would be around plus minus 2. Yeah? And here we see that the standard deviation is blown up by these 2 outlying observations. And therefore, we have to use robust estimates of the location and the scale. And what provides us with a robust measure of the location and the scale? That's the next question. The box plot. Yeah. So based on the box plot criterion, does this information contain outliers? And the answer will then be yes, and that will then be the smallest and the largest value. So let's have a look. So a box plot is based on what? Quantiles, and in particular quartiles. Yeah. So the quartiles divide the data into quarters. Yeah. So these are the 25th, the 50th, and the 75th quantile. Yeah. So let's have a look. This is the formula that's used for the location of the P percentile. Yeah, so the first quantile is the 25th percentile. So if you look at the location of the the 25th percentile, so that's equal to n minus 1. So n is the number of observations, 10 minus 1, that's 9. And we multiply it with converting the percentage points into percentage. So 0.35, and we add 1. So this is 9 quarters. So that's 2 quarter plus 1. So this should be 3.
Check.
So this means that the first quartile is based on observation with index 3.25. So what's this value, 3.25? Well, that's the value that is between the third and the fourth observation, but we use interpolation over here, linear interpolation. So if we look at the observation, so the third observation is equal to 3, and the fourth observation is equal to 4, so it should be between 3 and 4, and in this case, we take only a quarter of this interval. So the first quarter is defined as the third observation. And the third observation is equal to 3 plus then a quarter. That's over here. So now we're going to linear interpolate. A quarter times the difference between the fourth and the third observation. So the fourth observation is equal to 4, and the third observation is equal to 3. So this is equal to 3 1/4. Yeah, so this just uses linear interpolation, and due to the special structure of the data, in this case, this is equal. So the value is equal to the location. And this is not true in general, but due to the special structure of the data. Then we need the third quartile. Well, the third quartile, what is location? So that's then 9 times 3/4 plus 1, and that's equal to 7 3/4. So the third quartile is then the seventh observation, which is equal to 7, plus then the difference between the 8th and the 7th observation, and that times 3/4. And this, of course, gives us, due to the special structure of the data, this is also 7 3/4. So we have the first and third quartile. So that's over here. So we have the box. The box starts at the first quartile and ends at the third quartile. And it has a bar at the median. That's the third quartile. So what does this have to do with data being an outlying observation? Yeah, so first we have to calculate the difference, actually the length of the box, which is just the difference of the third and the first quartile. Yeah, so in this case, we look at the interquartile range. So the interquartile range is just the difference between the third quartile and the first quartile. So that's 7 3/4 minus 3 1/4. So this is equal to 4 and 1. These are nicely round numbers. So how many percent of the data is contained within this box? 50%. Yeah, because there are 75% of the data that is smaller than the third quarter, and 25% is smaller than the first quarter. So this contains the middle 50% of the data. So we have to calculate the lower bound and the upper bound.
I'm sorry, I'm missing the whole Q1 and then Q1 thing. That's that.
Yeah.
This is, I'm missing why there was 2 times Q1 and 2 times Q3. I'm sorry. So one was with an arrow and one was with an equal sign.
So first we have to determine the index.
Yeah.
So which value to take, and then we actually calculated this value. So first you have to look for the index.
So that must be a quarter. Yeah.
And then we look for the value that belongs to that particular index. Yeah. So you could multiply all these values by 2.
Yeah.
Then the index would still be the same. So let's say 3 1/4. But this would be 7 and this would be 8 then. But this would be 6 and this would be 8. So then you interpolate between 6 and 8. Yeah. We have to first determine where the cut is such that 25% is to the left hand side and 75% is to the right hand side. Yeah. Which index is this? The index of the value that's given by L, the location. So the location of the 25% is given by this number. Yeah. So if we multiply everything by 2, then we get -20, and then we get 4, 6, 8, 10, 12. So what are the rank numbers? The rank number 1, this is the smallest value, so this is rank number 1, this is rank number 2, 3, 4, 5, 6. Now if we look for the location of the first quarter, that's equal to 3 1/4.
Yeah,
Yeah,
because
so-
it's what you said. Okay. Yeah.
And then, so it should be between the 3rd and the 4th smallest observation. So then we take Q1 is equal to 6 plus, and then 1/4 times the difference between these two numbers, 8 minus 6. And this, of course, no surprise, is just 3 1/2. What? No. 6, 7. 7 because it was 3 1/4 times 2. That's 6 1/2. Let's see. Yeah, 6 1/2. It's just this number over here that we obtained originally multiplied by 2.
But when I was looking at the question this morning, I thought I'd learned somewhere that we would just go exactly between the 3 and the 4. We would just take 3 1/2 and make that. Is that I guess this is more.
Well, this is.
I seem to have learned it some point like that.
This is called linear interpolation. So if it happens to be a fraction and a half, then you are exactly at the middle, and you can just take the average, the unweighted average. So this can be viewed as a weighted average, and if you just take the 50% of the 3rd and the 50% of the 4th observation, that's just an equal weighted average. Yeah, so this is somewhat more precise, but of course, in real life, this would be determined by, let's say, Python, and it will actually do this automatically. So so this over here I looked up in the source code of the Python library, which calculates the quantile, and this was the formula used. So it could be that, for example, Python has a somewhat different, gives a different answer than SPSS or Excel.
I think what you're referring to is the second quartile, just way up in the middle. The 10
Yeah, could be.
Yeah, but, so it just determines whether, let's say, this over here is equal to a half or not. Yeah, so if it's equal to a half, then you can just take the sum and divide it by 2. You can just take it and weight it that way. So, well, we already we're not finished yet.
Oh, sorry.
So first of all, we should determine the lower bounds or the upper bounds. Yeah, so the lower bounds, whether something is an outlier and the upper bound. So let's have a look for the lower bounds. Lower bounds. Well, the lower bounds was equal to the first quarter minus 1.5 times the interquartile range. If you remember this from the first computer assignment, you also had to determine the lower and the upper bound. So in this case, the first quarter was equal to 3.25 minus 1.5 times the input range of 4.5, and this is equal to minus 3.5. Now, if you compare the observations with this lower bound, then you can clearly see that there is one outlying observation because the first observation is smaller than the lower bound. Yeah, so in this case, the conclusion would be that minus 10 is an outlier. Then, to the right-hand side, we have to calculate the upper bound. So the upper bound is just the third quarter plus 1.5 times the input range. In this case, it's 7.75 plus 1.5 times 4.5, and that's equal to 14.5. Yeah. For this case, we clearly see that the largest observation is specified as an outlier. And then, of course, C, explain the difference between 2A and 2B. Which procedure do you prefer and why? So the difference is that the second procedure is based on robust measures of the location and the scale. And if you don't use these robust measures, then these two outlying observations are masked. Yeah, so we had this terminology in the isolation trees. So it could be that due to the outlying or the extreme values, the mean, and in this case, especially the standard deviation, is blown up so much that the outlying observations are not visible anymore. They are, in a sense, they are masked. And we saw this term in this paper in the last lecture. Masking means that they are not visible anymore due to the fact that this standard deviation is heavily influenced by these two outlying observations. So, Any questions related to this exercise? So,
You also put answers online?
yeah. So if I want to be somewhat nasty, then I could scramble the data in such a way that you first have to rank the data from small to large. Yeah. So if you calculate this over here, this location, then of course this is the location of the ordered data. So if it's unordered, you first have to order the data. That's how it was nice to last year's student group. We will see. Okay, then quite small question. What's the difference between taking row percentages and taking column percentages in a contingency table? You may use the table below as an example, and this is exactly the table we have seen in the churn example. Yeah, so this is a contingency table, and in a contingency table we see frequencies. So we can calculate the column percentages and the row percentages. So if we look at column percentages, we get the following numbers. And if we consider row frequencies, we get a different table. So who wants to give it a shot? So this over here, this 42.4%, how can it be interpreted? Yeah. Yeah. So this is the conditional probability that people churned. So churn is yes, given that they have a subscription to the international plan. So let's say international plan is equal to yes. Yeah, that's this over here. In this case, it's an estimated probability because this is just a approximation. So let's have a look over here. This 28.4%. This is then another conditional probability. Yeah, so this is the conditional probability that someone has a subscription to the international plan, given that someone has churned. Yeah, so these are very different conditional probabilities, and in this case, the variable of interest is whether a person has churned or not. So this, if we take the column percentages, is then the, in a sense, correct way to look at the data. Yeah, we are interested in explaining the probability of churning given the characteristics of a particular person. Yeah? whether someone has a subscription to the international plan, yes or no, whether someone has a subscription to the voicemail, and we had another of other characteristics, the number of day minutes, evening minutes, night minutes, etc. Yeah? Any questions? Okay, then the fourth question. So the questions follow the structure of the course of the lectures. So we started off with the crisp data mining schedule. Then we went to identifying outlying observations in the univariate setting. Then we did some exploratory data analysis using these contingency tables, looking in this case at column percentages, and then we looked at, for example, transformations. So if the data is non-normally distributed, we first of all would like a measure of how normal the data is distributed, and one non-normal feature is, for example, a skewness different from 0. Yeah, so we know that normally distributed random variables distributions have a skewness of 0, and the skewness of 0 means that the distribution is symmetric. Yeah? So that has to do with the third moment, and we could also look at the fourth moment, and that's then the kurtosis. Yeah? We could have axis kurtosis or somewhat, that has to do with the tails, fatter tails or thinner tails. But that's a topic which we didn't discuss in this course. So we only looked at the skewness, and in this case, this was a very easy estimate measure of the skewness. It's just the difference between the mean and the median transformed. So we multiply the difference by 3, and then we divide by the standard deviation. So the first question is then, why this is a good measure for the skewness of a distribution? Or stated otherwise, why does this give a positive number if the data is positively skewed, and gives it a negative number if it is negatively skewed? Well, if a distribution is symmetrically distributed, so if it has a symmetric shape, then we know that the mean and the median are equal. Okay? So then the mean is equal to the median. So what do we know for a positively skewed distribution? So then here is the median, and over here will be the mean. Yeah, and the mean, of course, is pulled to the right-hand side due to these values on the right tail. Yeah, so if it is positively skewed, we know that the sample mean is larger than the median, and therefore this difference will be positive. Yeah, so then the difference will be positive. If we are looking at data which is negatively skewed, and 50% of the data is over here, that's the median, and then this is the mean. We just have the mirror image. So in this case, we see that the sample mean is smaller than the median. So this is smaller than the median, so this means that the difference between the two is negative. So the sign of this difference is determined whether it's positively skewed or negatively skewed. It is positive or negative numbers. Then give 3 different transformations that could help to achieve a less skewed distribution. So, which transformations did we consider? Yeah, the log transformation. So you could, for example, have y, or let's say z, is the log of y. That's one transformation. Yeah, we have looked at the square root of y. And we also have looked at least in the lecture, at 1 over the square root. So that's B. And then C. Can we always apply these transformations? So this was also the case in the second assignment. So in the second assignment, you had these negative values. Yeah? If you recall, we had this in this shop, we had this negative sales values for particular persons who returned items. So then we first had to take the absolute value. In this case, the log and the square root, they require what kind of condition? So these two require that y is larger than 0. And this requires that y is at least 0. Yeah, so the square root of 0, that's well defined. But the logarithm of 0, that's minus infinity. And divided by 0 leads also to not a number. Yeah, it leads to plus infinity. Then D, suppose you want to predict the target variable y. However, the variable y is highly skewed. But luckily, there's a transformation denoted by z, which is almost symmetrically distributed. Are you finished when a model is trained for z? Yeah, so we have y. We take a transformation such that the z is almost, let's say, like a normal distribution. Then we make a model for this z, and then we are applying the model, and this gives us, let's say, a predicted value for z. Are we then finished? Yeah, we have to transform it back into y, because y is the variable we want to predict. Yeah, so in this case, if we want to predict y, in this case, y hat is the exponent of z hat. If you take the square root, then you have to consider the squared value. And if we take this, then you have to solve for y. Then y hat is, let's see, 1 over square root of z hat. Yeah, so only one of the examples is sufficient. So I think second transformation, that's the easiest one. But yeah, I think not many, well, I think half of the students got this right. So this was considered as a, let's say, somewhat difficult question. I don't know why, but let's have a look at then the fifth question. Why might an analyst prefer the exploratory data analysis over hypothesis testing when doing data mining?
What's exactly what captured in the word data mining? What's captured in the word data mining? Is that like the whole process you just saw, or?
Yeah, so in this case, it explicitly refers to the exploratory data analysis, and the exploratory data analysis is in the second and the third
Yeah, and
phase.
that's a form of data mining, and data mining is more like a.
Data mining is like recovering patterns in the data.
So that's a part of the process. But I'm finding it hard to put the word data mining. Like it's not in the processes we saw, but it does come back in.
Yeah, so data mining itself is finding, let's say, patterns in the data, which we could use to predict.
So that's that in the third part of the process in the beginning. In the first question.
Yeah, so over here, so, but the whole, let's say, the whole life cycle has an aim of, let's say, data mining.
Okay.
Yeah, so we want to answer the question, and that's usually done by doing some data mining activities. And in this case, let's say the exploratory data analysis, that's over here in the data understanding phase.
So it is something like bigger and.
Yeah, so data mining, that's bigger. So this is the CRISP. So the M stands for data mining. So let's say data mining in the definition of that the book uses is just to see whether we can recover patterns in the data, which we can use to make predictions, and that usually answers then a specific research question.
Should it be used for the machine learning as well? Because I've seen CRISP DM being used for machine learning phase as well. So for machine learning model development.
Yeah. Well, but I mean,
TM
this so in the modeling phase, this is where the machine learning part comes in these two phases.
Right.
Yeah. So let's say machine learning, that's part of the greater life cycle. So, for example, we have seen decision trees.
Yeah.
So, in these decision trees, that's only one small tool from machine learning.
Okay. Which is part of the modeling phase.
Yeah, of the modeling phase. You saw that when, for example, we did imputation, we actually used already some of the modeling techniques to impute the missing values. Yeah, and therefore, there are all kinds of interactions between all these phases. So, the question is actually, so whether an analyst prefers EDA above, let's say, hypothesis testing. Yeah, so that was the other option. So the question is not really clear on this point, but, well, in the context of this course, there's only one possible answer. What?
Find correlations.
To find correlations, yeah. So what's different from finding correlations and doing hypothesis testing?
Without finding knowledge.
Yeah. So it's more open-minded, and first of all, this hypothesis testing is usually only in a limited setting applicable. Yeah, so if you have a limited number of variables, well, you already saw in the assignments that if you consider quite small data set, that the number of variables is already, let's say, around 30. Yeah, Yeah. So if you have a lot of variables, then you might prefer, let's say, EDA above hypothesis testing, because in a sense it's more open-minded, so you can then recover the, let's say, patterns between different variables. Yeah, so if you have a lot of predictors, or the analyst is really unfamiliar with the data, or there's not much literature. Yeah, so normally in economics, we have a special question in mind, and then you have a particular theory. Yeah, so if you are interested in financial questions, then you have the whole field of subdiscipline of finance. If you are interested in let's say, individual behavior, then that's something like microeconometrics. If you want to do something more on an aggregate scale, that's the domain of macroeconomics. So, especially, for example, in marketing, in the marketing field, there are not many theories. So you just have to see for yourself what are interesting subsets. So in this case, consider the scatter plot above. So this is just one of the scatter plots from the book. And it's plots the day minutes versus the evening minutes, which is just this straight line over here. And what we see is that the number of red spots over here, so the number of red dots indicate people who churn, is a lot more visible above the line than below the line. So this could be, let's say, an interesting subset. Let's have a look. So this is the picture. So what's here on the above this line? So these are people that have a high value for the day minutes, but also a high value of the evening minutes. Yeah. So these are really frequent callers, not only during the day, but also during the evening. So then we introduce this flag variable or dummy variable, which is 1 if it is above the line and 0 if it is below the line. And then we have this contingency table. So this is the contingency table with frequencies. And then it says compare the churning rates, where rates is in italics. Yeah, so you have to convert the frequencies into rates. So compare the churning rates of the groups for which the flag variable is 1 versus 0. Yeah? So now there are two options. You could either take the column percentages or the row percentages. Yeah, so that's where some students struggle with. So in this case, we are interested in predicting the churning rates. So do we consider column or row percentages? Column percentages. Yeah. So looking at the column percentages, we are looking over here for people who churned. So churn is true then. Churn is true. So what are then the column percentages? 11% versus 17.4%. So this is for the dummy, for the flag variable being 0 and 1. So if we so these are rates, yeah. So these are percentages. If we compare the rates, so 74 divided by 11%, well, this is, let's say, around 6. Yeah. So This is almost 6 times as large as the churning rate below the line. Yeah, so this indeed is an interesting group because they have a 6-fold churning rate than the people that are below the line. So based on your outcome of this sub-question, would you advise the company to focus exclusively on this group of customers? Yeah, and perhaps you even recognize the sentence is just literally from the copy from the book. Yeah, so I have PDF, copy, paste. And I have another question. So, what does the book say? Well, if we look at the number of people that are above the line, 200 out of more than 3,000. Yeah, so the size of this group is really, really limited. Yeah, so this, of course, also has to do with why we always have, let's say, histogram, overlay histogram in absolute frequency and normalized. So sometimes you could identify groups in which the churning rate is really, really high, but the number of customers is really, really limited. Yeah, so of course you can focus on this subgroup, but not exclusively, because they are only a small part of all the customers that have churned away. Welcome. You're in time for the break.
Yeah.
Yeah, so I suggest that we take a break, and after the break, we'll have a look at the remaining questions. So it's actually watching. Yeah, I think Bernard. Bernard right there at the corner. I think. Online gangster.
Peter, few guys are watching.
Huh?
Few guys are watching. Yeah,
Oh.
Peter, Vincent.
Yeah, even a few. Yeah.
So I did be about the problem with
Oh, okay. Yeah.
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 Take a look.